Hey everyone, it's Dr. Walker. Let's look at another example from v061C on angular momentum. This one is a collision of a bullet with a cylinder. We're given the mass and the velocity of the bullet, and then we're given the mass and the radius of the cylinder, which is initially at rest. Once they collide, then the bullet becomes embedded and then moves with the cylinder. We want to know what is the angular velocity of the cylinder just after this collision, which is also the angular velocity of the bullet since they are stuck together. Whenever we have a collision and we have rotational motion, we want to think about using conservation of angular momentum. In order to use conservation of angular momentum, which says that the initial momentum, angular momentum, equals the final angular momentum, we have to make sure that there are no net external torques acting on the system. The system is going to be the bullet and the cylinder. Well, the problem says that there's no frictional torque here from the interaction. And then we know that the weight of each object acts through the center of through the axis of rotation. So we know that they don't exert any torque either. So we have an isolated system. We can use conservation of angular momentum. The initial angular momentum only has to do with the bullet since it's the only thing moving. The bullet is a particle, so we can use the MVR definition. And that is because it is moving with a velocity v that is perpendicular to the position vector r. R goes from the axis of rotation up to where the bullet is. That's our position vector, so they're perpendicular to each other. We know that the angular momentum is going to be mvr. And I'm using little m for the mass of the bullet, v because we're given its initial velocity, and now the r, I'm actually going to put r naught, right? The radius of the cylinder, that is the distance from the axis to where the particle is. And now we need to find our final angular momentum. Think of this object, the cylinder is rotating with the bullet embedded in it. So just think of it as one big rotating object and think about using the definition I omega, since we're looking for final angular velocity anyway. We just need the moment of inertia of the cylinder and the bullet together. Let's do that on the side. The moment of inertia of the bullet and the cylinder together. Well, the bullet is just a particle, so we use the mr squared definition, where r is r naught. It's the distance from the axis to where the mass is. So this is for the bullet. And then we have to add the moment of inertia of the cylinder, which is a solid disk and has a moment of inertia 1/2 mr squared, where once again we use r naught for the radius. So we can plug in this moment of inertia into our angular momentum conservation equation. We're going to have mvr naught equals mr naught squared plus 1/2 capital M r naught squared times omega final. And now we can solve for omega final. Omega final equals mv r naught over, and we can factor out the r naught squared here, r naught squared times m plus 1/2 m. So we can see that one of the r naughts cancels out, and then we can plug in our values. 0.002 kilograms, we're converting this to kilograms here, times our velocity of 500 meters per second, divided by the radius, which was 0.5, times the mass, 0.002 plus 1/2 of the big mass, which is 3.2. We plug in all of these values, and we get 1.2 radians per second. So that is the magnitude of the angular velocity. Technically, it definitely has a direction. I've kind of been neglecting the directions all throughout. And that's because the direction, if we look at the direction of rotation, which is clockwise, we use the right-hand rule where we curl our fingers in the direction of omega. So you curl your fingers clockwise, and you'll see that the thumb points into the page. So that is technically the direction. But we can just pretend that it was asking us for the magnitude of the angular velocity, so that we can just say 1.2 radians per second is our answer. Technically, when we are setting up the equation here, we do have to pay attention to direction. It turns out that the angular momentum of the particle here, of the bullet, was also into the page. If you point your fingers upward, fold them to the right. So you put them upward for R and fold them for V, and the thumb is into the page. So all of the angular momenta were into the page, so we were okay kind of neglecting their direction until the very end. So this was an example of using conservation of angular momentum for a collision that involved rotational motion.